Okay, so I'm going to talk today about levers, and this is some of the background knowledge you're going to want to have for the Strong Arm mission covering forces and simple machines. So I've got a level that I got from the garage. I've marked lines along this level. You could use a ruler, anything long and flat, but it's nice to mark some different distances. So what I've done here is I've marked the center point, and to the left and right of the center point I've marked 8 centimeters, 12 centimeters, 16 and 24 on one side, and 8, 12, 16 and 24 on the other. I'm going to just put this level with its center over something that has a little bit of width to it, okay? The narrower this little platform is, the harder it's going to be to get this thing to balance. So it's okay to have a little bit of width here. It's going to make your demonstration go a little smoother. I've got some weights here, and just for a standard weight I've used a tuna can. And let's just start by balancing our level like this. So what I'm doing is I'm putting one tuna can at 24 on this side, one tuna can at 24 on this side. The weight of the tuna can times the distance from the pivot point is what tells you how much twisting force there's going to be. And if the twisting force this way balances the twisting force this way, our level is going to stay flat. So 1 times 24 equals 1 times 24. If we move this one in to 12, you can see that there's a net force twisting the lever down, okay? Because 1 times 24 is way bigger than 1 times 12. So you have that net twisting force. So if you're an astronaut and you're applying a force to one side of a lever and you want to have 3 times as much force on the other side of the lever, you have to play around with the distances where it is that your lever is working. We can see that by having 1 tuna can times 24 here. 1 times 24 is equal to 2 times 12. So if we bring 2 tuna cans in at 12 centimeters, that balances 1 at 24. 1 times 24 is equal to 3 times 8. So if we have 3 tuna cans at 8 centimeters, that balances the 1 tuna can at 24. So for our astronauts, if they are applying a force and they want to get 3 times the amount of force on the other side of their lever, then they have to be 3 times further away from the pivot point than where the Canadarm joint is. So if you imagine the joint of the Canadarm is at 8 meters, let's say, from a pivot point, then the astronaut has to be at 24 meters, and that way, if the astronaut applies a force, there's going to be 3 times more force on the other side of the pivot point. And that's the answer that we're looking for from our students. Thank you.